Chapter 5 Continuity and Differentiability. Continuity. We start the section with two informal examples to get a feel of continuity. Consider the function f of x is equal to 1 if x is less than or equal to 0, 2 if x is greater than 0. This function is of course defined at every point of the real line. Graph of this function is given in the figure. One can deduce from the graph that the value of the function at nearby points on x-axis remain close to each other except at x is equal to 0. At the points near and to the left of 0, that is, at points like minus 0.1, minus 0.01, minus 0.001, the value of the function is 1. At the points near and to the right of 0, that is, at points like 0.1, 0.01, 0.001, the value of the function is 2. Using the language of left and right hand limits, we may say that the left, respectively right hand limit of f at 0 is 1, respectively 2. In particular, the left and right hand limits do not coincide. We also observe that the value of the function at x is equal to 0 coincides with the left hand limit. Note that when we try to draw the graph, we cannot draw it in one stroke. That is, without lifting pen from the plane of the paper. We cannot draw the graph of this function. In fact, we need to lift the pen when we come to 0 from left. This is one instance of function being not continuous at x is equal to 0. Now, consider the function defined as f of x is equal to 1 if x is not equal to 0, 2 if x is equal to 0. This function is also defined at every point. Left and the right hand limits at x is equal to 0 are both equal to 1, but the value of the function at x is equal to 0 equals 2. Which does not coincide with the common value of the left and right hand limits. Again, we note that we cannot draw the graph of the function without lifting the pen. This is yet another instance of a function being not continuous at x is equal to 0. Naively, we may say that a function is continuous at a fixed point if we can draw the graph of the function around that point without lifting the pen from the plane of the paper. Mathematically, it may be phrased precisely as follows. Definition 1. Suppose f is a real function on a subset of the real numbers and let C be a point in the domain of f. Then f is continuous at C. If limit x tends to C, f of x is equal to f of C. More elaborately, if the left hand limit, right hand limit and the value of the function at x is equal to C exist and equal to each other, then f is said to be continuous at x is equal to C. Recall that if the right hand and left hand limits at x is equal to C coincide, then we say that the common value is the limit of the function at x is equal to C. Hence, we may also rephrase the definition of continuity as follows. A function is continuous at x is equal to C if the function is defined at x is equal to C, and if the value of the function at x is equal to C equals the limit of the function at x is equal to c. If f is not continuous at c, we say f is discontinuous at c, and c is called a point of discontinuity of f. Example 1. Prove that the function f of x is equal to 5x minus 3 is continuous at x is equal to 0, x is equal to minus 3 and x is equal to 5. Solution: f of x is equal to 5x minus 3. At x is equal to 0, f of 0 is equal to 5 into 0 minus 3 is equal to minus 3. Limit x tends to 0, f of x is equal to limit x tends to 0, 5x minus 3 is equal to 5 into 0 minus 3 is equal to minus 3. Thus, limit x tends to 0, f of x is equal to minus 3 is equal to f of 0. The function f of x is continuous at x is equal to 0. F of minus 3 is equal to 5 into minus 3 minus 3 is equal to minus 18 at x is equal to minus 3. Limit x tends to minus 3, f of x is equal to limit x tends to minus 3, 5x minus 3 is equal to 5 into minus 3 minus 3 is equal to minus 18. Thus, limit x tends to minus 3, f of x is equal to minus 18 is equal to f of minus 3. The function f of x is continuous at x is equal to minus 3. F of plus 5 is equal to 5 into 5 minus 3 is equal to 22 at x is equal to 5. Limit x tends to 5, f of x is equal to limit x tends to 5, 5x minus 3 is equal to 5 into 5 minus 3 is equal to 22. Thus, limit x tends to 5, f of x is equal to 22 is equal to f of 5. The function f of x is continuous at x is equal to 5. Example 2. Check the continuity of the function f of x is equal to 1 upon x minus 5, where x is not equal to 5. Solution: suppose a belongs to R, where a is not equal to 5. Limit x tends to a plus f of x is equal to limit h tends to 0, 1 upon a plus h minus 5 is equal to 1 upon a minus 5. Limit x tends to a minus f of x is equal to limit h tends to 0, 1 upon a minus h minus 5 is equal to 1 upon a minus 5. F of a is equal to 1 upon a minus 5. Limit x tends to a plus f of x is equal to limit x tends to a minus f of x is equal to f of a. The function f of x is equal to 1 upon x minus 5 is continuous at every point except x is equal to 5. For x is equal to 5, limit x tends to 5 plus f of x is equal to plus infinity, and limit x tends to 5 minus f of x is equal to minus infinity. Plus infinity and minus infinity are not real numbers. Therefore, the left and right hand side limits does not exist at x is equal to 5. Function f is discontinuous at x is equal to 5. Example 3. Constant function f of x is equal to k. Check at which point is continuous. Solution: the function is defined at all real numbers and by definition its value at any real number equals k. Let c be any real number. Then limit x tends to c f of x is equal to limit x tends to c k is equal to k. Since f of c is equal to k is equal to limit x tends to c f of x for any real number c. The function f is continuous at every real number. Example 4. Prove that the identity function on real numbers given by f of x is equal to x is continuous at every real number. Solution: the function is clearly defined at every point and f of c is equal to c for every real number c. Limit x tends to c, f of x is equal to limit x tends to c, x is equal to c. Thus, limit x tends to c, f of x is equal to c is equal to f of c, and hence the function is continuous at every real number. Definition 2. A real function f is said to be continuous if it is continuous at every point in the domain of f. This definition requires a bit of elaboration. Suppose f is a function defined on a closed interval a, b. Then for f to be continuous, it needs to be continuous at every point in closed interval a, b, including the endpoints a and b. Continuity of f at a means limit x tends to a plus f of x is equal to f of a, and continuity of f at b means limit x tends to b minus f of x is equal to f of b. Observe that limit x tends to a minus f of x and limit x tends to b plus f of x do not make sense. As a consequence of this definition, if f is defined only at one point, it is continuous there. That is, if the domain of f is a singleton, f is a continuous function. Example 5. Is the function defined by f of x is equal to modulus of x minus 5 a continuous function? Solution: suppose a belongs to R. Limit x tends to a plus f of x is equal to limit x tends to a plus modulus of x minus 5 is equal to limit h tends to 0 modulus of a plus h minus 5 because of x is equal to a plus h is equal to modulus of a minus 5 is equal to a minus 5. Limit x tends to a minus f of x is equal to limit x tends to a minus modulus of x minus 5 is equal to limit h tends to 0 modulus of a minus h minus 5 is equal to modulus of a minus 5 is equal to a minus 5. Limit x tends to a plus f of x is equal to limit x tends to a minus f of x is equal to f of a. Therefore, f of x is equal to modulus of x minus 5 is a continuous function. Note, x minus 5 is continuous since it is a polynomial function. Therefore, modulus of x minus 5 it is a continuous function. Example 6. Discuss the continuity of the function f given by f of x is equal to x cube plus x square minus 1. Solution: clearly f is defined at every real number c and its value at c is f of c is equal to c cube plus c square minus 1. We also know that limit x tends to c, f of x is equal to limit x tends to c, x cube plus x square minus 1 is equal to c cube plus c square minus 1. Thus, limit x tends to c, f of x is equal to f of c, and hence f is continuous at every real number. This means f is a continuous function. We take this opportunity to explain the concept of infinity. This we do By analyzing the function f of x is equal to 1 upon x near x is equal to 0. To carry out this analysis, we follow the usual trick of finding the value of the function at real numbers close to 0. Essentially, we are trying to find the right-hand limit of f at 0. We tabulate this in the following. We observe that as x gets closer to 0, from the right, the value of f of x shoots up higher. This may be rephrased as the value of f of x may be made larger than any given number by choosing a positive real number very close to 0. In symbols, we write limit x tends to 0 plus f of x is equal to plus infinity, to be read as the right-hand limit of f of x at 0 is plus infinity. We wish to emphasize that plus infinity is not a real number and hence the right-hand limit of f at 0 does not exist as a real number. Similarly, the left-hand limit of f at 0 may be found. The following table is self-explanatory. From the table, we deduce that the value of f of x may be made smaller than any given number by choosing a negative real number very close to 0. In symbols, we write limit x tends to 0 minus f of x is equal to minus infinity, to be read as the left-hand limit of f of x at 0 is minus infinity. Again, we wish to emphasize that minus infinity is not a real number and hence the left-hand limit of f at 0 does not exist as a real number. The graph of the reciprocal function given in figure is a geometric representation of the above mentioned facts. Example 7. Discuss the continuity of the function f defined by f of x is equal to x plus 2, where x is less than or equal to 1, x minus 2, where x is greater than 1. Solution. The function f is defined at all points of the real line. Case 1. If c is less than 1, then f of c is equal to c plus 2. Therefore, limit x tends to c, f of x is equal to limit x tends to c, x plus 2 is equal to c plus 2. Thus, f is continuous at all real numbers less than 1. Case 2. If c is greater than 1, then f of c is equal to c minus 2. Therefore, limit x tends to c, f of x is equal to limit x tends to c, x minus 2 is equal to c minus 2 is equal to f of c. Thus, f is continuous at all points x is greater than 1. Case 3. If c is equal to 1, then the left-hand limit of f at x is equal to 1 is limit x tends to 1 minus f of x is equal to limit x tends to 1 minus x plus 2 is equal to 1 plus 2 is equal to 3. The right-hand limit of f at x is equal to 1 is limit x tends to 1 plus f of x is equal to limit x tends to 1 plus x minus 2 is equal to 1 minus 2 is equal to minus 1. Since the left and right hand limits of f at x is equal to 1 do not coincide, f is not continuous at x is equal to 1. Hence, x is equal to 1 is the only point of discontinuity of f. The graph of the function is given in figure. Example 8. Find all the points of discontinuity of f where f is defined by f of x is equal to modulus of x plus 3, where x is less than or equal to minus 3, minus 2x, where minus 3 is less than x is less than 3, 6x plus 2, where x is greater than or equal to 3. Solution: the function f of x is defined for each x belongs to R. At x is equal to minus 3, therefore, limit x tends to 3 minus f of x is equal to limit x tends to 3 minus f of x is equal to limit x tends to 3 minus modulus of x plus 3 is equal to limit h tends to 0 modulus of minus 3 minus h plus 3 is equal to 3 plus 3 is equal to 6. Therefore, limit x tends to 3 plus f of x is equal to limit x tends to 3 plus minus 2x is equal to limit h tends to 0 minus 2 into minus 3 plus h is equal to limit h tends to 0 6 minus 2h is equal to 6. f of minus 3 is equal to modulus of minus 3 plus 3 is equal to 3 plus 3 is equal to 6. Therefore, limit x tends to 3 plus f of x is equal to limit x tends to 3 minus f of x is equal to f of minus 3. Function f of x is continuous at x is equal to minus 3. At x is equal to 3, therefore, limit x tends to 3 minus f of x is equal to limit x tends to 3 minus minus 2x is equal to limit h tends to 0 minus 2 into 3 minus h is equal to limit h tends to 0 minus 6 plus 2h is equal to minus 6. Therefore, limit x tends to 3 plus f of x is equal to limit x tends to 3 plus 6x plus 2 is equal to limit h tends to 0 6 into 3 plus h plus 2 is equal to limit h tends to 0 18 plus 3h plus 2 is equal to 20. Therefore, limit x tends to 3 minus f of x is not equal to limit x tends to 3 plus f of x. The function f of x is discontinuous at x is equal to 3. Algebra of continuous functions. Since continuity of a function at a point is entirely dictated by the limit of the function at that point, it is reasonable to expect results analogous to the case of limits. Theorem 1. Suppose f and g be two real functions continuous at a real number c. Then, number 1, f plus g is continuous at x is equal to c. Number 2, f minus g is continuous at x is equal to c. Number 3, f into g is continuous at x is equal to c. Number 4, f upon g is continuous at x is equal to c, provided g of c is not equal to 0. Proof: we are investigating continuity of f plus g at x is equal to c. Clearly, it is defined at x is equal to c. We have limit x tends to c, f plus g of x is equal to limit x tends to c, f of x plus g of x. By definition of f plus g is equal to limit x tends to c, f of x plus limit x tends to c, g of x by the theorem of limits is equal to f of c plus g of c, as f and g are continuous, is equal to f plus g of c by definition of f plus g. Hence, f plus g is continuous at x is equal to c. Proofs for the remaining parts are similar and left as an exercise to the reader. Remarks. Number 1. As a special case of 3 above, if f is a constant function, that is, f of x is equal to lambda for some real number lambda, then the function lambda into g defined by lambda into g of x is equal to lambda into g of x is also continuous. In particular, if lambda is equal to -1, the continuity of f implies continuity of -f. Number 2. As a special case of 4 above, if f is the constant function, f of x is equal to lambda, then the function lambda upon g defined by lambda upon g of x is equal to lambda upon g of x is also continuous wherever g of x is not equal to 0. In particular, the continuity of g implies continuity of 1 upon g. The above theorem can be exploited to generate many continuous functions. They also aid in deciding if certain functions are continuous or not. Example 1. Discuss the continuity of cosine function. Solution: f of x is equal to cos x, where x belongs to R. Suppose c is a real number. Limit x tends to c, f of x is equal to limit x tends to c cos x is equal to limit h tends to 0 cos c plus h is equal to limit h tends to 0 cos c into cos h minus sin c into sin h is equal to cos c into 1 minus sin c into 0 is equal to cos c is equal to f of c. Therefore, f of x is equal to cos x is continuous for c belongs to R. Since c is an arbitrary real number, therefore f of x is equal to cos x is continuous function. Example 2. Prove that the function f of x is equal to cot x is equal to 1 upon tan x, where x belongs to R minus set of n pi, where n belongs to I, is continuous. Solution: suppose c belongs to R minus set of n pi, where n belongs to I. Limit x tends to c, f of x is equal to limit x tends to c 1 upon tan x is equal to limit h tends to 0 1 upon tan c plus h is equal to limit h tends to 0 1 minus tan c into tan h upon tan c plus tan h is equal to 1 minus tan c into tan 0 upon tan c plus tan 0, because of tan 0 is equal to 0 is equal to 1 upon tan c is equal to cot c is equal to f of c. Therefore, f of x is equal to cot x is a continuous function for c belongs to R minus set of n pi, where n belongs to I. Therefore, f of x is equal to cot x is a continuous function. Theorem 2. Suppose f and g are real valued functions such that f of g is defined at c. If g is continuous at c and if f is continuous at g of c, then f of g is continuous at c. Example 3. Prove that the function f of x is equal to cos x square is a continuous function. Solution: h of x is equal to x square, where x belongs to R, is continuous since it is a polynomial function, and g of x is equal to cos x, where x belongs to R, is constant as it is a trigonometric function. Compound function GOH of h is equal to g of h of x is equal to g of x square. F of x is equal to cos x square. Now, since the functions h and g are continuous functions for x belongs to R, then their composition function GOF of x is also continuous function. Therefore, f of x is equal to cos x square is a continuous function. Differentiability. Suppose f is a real function and c is a point in its domain. The derivative of f at c is defined by limit h tends to 0, f of c plus h minus f of c upon h. Provided this limit exists, derivative of f at c is denoted by f dash of c or d by dx f of x at x is equal to c. The function defined by f dash of x is equal to limit h tends to 0, f of x plus h minus f of x upon h. Wherever the limit exists is defined to be the derivative of f. The derivative of f is denoted by f dash of x or d by dx f of x, or if y is equal to f of x by dy by dx or y dash. The process of finding derivative of a function is called differentiation. We also use the phrase differentiate f of x with respect to x to mean find f dash of x. The following rules were established as a part of algebra of derivatives. Number 1. U plus or minus v whole dash is equal to u dash plus or minus v dash. Number 2. uv whole dash is equal to u dash v plus uv dash, which is Leibniz or product rule. Number 3. u upon v whole dash is equal to u dash v minus uv dash upon v square, wherever v is not equal to 0, which is quotient rule. The following table gives a list of derivatives of certain standard functions. Whenever we defined derivative, we had put a quotient provided the limit exists. Now, the natural question is, what if it doesn't? The question is quite pertinent, and so is its answer. If limit h tends to 0, f of c plus h minus f of c upon h does not exist, we say that f is not differentiable at c. In other words, we say that a function f is differentiable at a point c in its domain if both limit h tends to 0 minus f of c plus h minus f of c upon h and limit h tends to 0 plus f of c plus h minus f of c upon h are finite and equal. A function is said to be differentiable in an interval closed interval a, b, if it is differentiable at every point of closed interval a, b. As in case of continuity, at the endpoints a and b, we take the right hand limit and left hand limit, which are nothing but left hand derivative and right hand derivative of the function at a and b respectively. Similarly, a function is said to be differentiable in an interval open interval a, b, if it is differentiable at every point of open interval a, b. Theorem 3. If a function f is differentiable at a point c, then it is also continuous at that point. Proof. Since f is differentiable at c, we have limit x tends to c f of x minus f of c upon x minus c is equal to f dash of c. But for x is not equal to c, we have f of x minus f of c is equal to f of x minus f of c upon x minus c into x minus c. Therefore, limit x tends to c f of x minus f of c is equal to limit x tends to c f of x minus f of c upon x minus c into x minus c. Therefore, limit x tends to c f of x minus limit x tends to c f of c is equal to limit x tends to c f of x minus f of c upon x minus c into limit x tends to c x minus c is equal to f dash of c into 0 is equal to 0. Therefore, limit x tends to c f of x is equal to f of c. Hence, f is continuous at x is equal to c. Corollary 1. Every differentiable function is continuous. We remark that the converse of the above statement is not true. Indeed, we have seen that the function defined by f of x is equal to modulus of x is a continuous function. Consider the left hand limit minus limit h tends to 0 minus f of 0 plus h minus f of 0 upon h is equal to limit h tends to 0 minus h upon h is equal to minus 1. The right hand limit h tends to 0 plus f of 0 plus h minus f of 0 upon h is equal to limit h tends to 0 plus h upon h is equal to 1. Since the above left and right hand limits at 0 are not equal, limit h tends to 0 f of 0 plus h minus f of 0 upon h does not exist, and hence f is not differentiable at 0. Thus, f is not a differentiable function. Derivatives of composite functions. To study derivative of composite functions, we start with an illustrative example. Say, we want to find the derivative of f, where f of x is equal to 2x plus 1 whole cube. One way is to expand 2x plus 1 whole cube using binomial theorem and find the derivative as a polynomial function as illustrated below. d by dx f of x is equal to d by dx 2x plus 1 whole cube is equal to d by dx 8x cube plus 12x square plus 6x plus 1 is equal to 24x square plus 24x plus 6 is equal to 6 into 2x plus 1 whole square. Now, observe that f of x is equal to HOG of x, where g of x is equal to 2x plus 1 and h of x is equal to x cube. Put t is equal to g of x is equal to 2x plus 1. Then f of x is equal to h of t is equal to t cube. Thus, df by dx is equal to 6 into 2x plus 1 whole square is equal to 3 into 2x plus 1 whole square into 2 is equal to 3t square into 2 is equal to dh by dt into dt by dx. The advantage with such observation is that it simplifies the calculation in finding the derivative of, say, 2x plus 1 whole raised to 100. We may formalize this observation in the following theorem called the chain rule. Theorem 4. Chain rule. Let f be a real-valued function which is a composite of two functions u and v. That is, f is equal to VOU. Suppose t is equal to u of x, and if both dt by dx and dv by dx exist, we have df by dx is equal to dv by dt into dt by dx. Chain rule may be extended as follows. Suppose f is a real-valued function which is a composite of three functions u, v and w. That is, f is equal to WOU OV if t is equal to v of x and s is equal to u of t, then df by dx is equal to d of WOU by dt into dt by dx is equal to dw by ds into ds by dt into dt by dx, provided all the derivatives in the statement exist. Example 1. Differentiate the function with respect to x in sin x square plus 5. Solution: y is equal to sin x square plus 5. Let u is equal to x square plus 5. U is equal to x square plus 5. Therefore, y is equal to sin u, or u is equal to x square plus 5. Therefore, dy by du is equal to d by dx sin u is equal to cos u. Du by dx is equal to d by dx x square plus 5 is equal to d by dx x square plus d by dx 5 is equal to 2x plus 0 is equal to 2x. Now, according to the chain rule, dy by dx is equal to dy by du into du by dx is equal to cos u into 2x is equal to cos x square plus 5 into 2x because of u is equal to x square plus 5 is equal to 2x into cos x square plus 5. Example 2. Find the derivative of tan 2x plus 3. Solution: let f of x is equal to tan 2x plus 3. U of x is equal to 2x plus 3 and v of t is equal to tan t. Then VOU of x is equal to v of u of x is equal to v of 2x plus 3 is equal to tan 2x plus 3 is equal to f of x. Thus, f is a composite of two functions. Put t is equal to u of x is equal to 2x plus 3. Then dv by dt is equal to sec square t and dt by dx is equal to 2 exist. Hence, by chain rule, df by dx is equal to dv by dt into dt by dx is equal to 2 sec square 2x plus 3. Derivatives of implicit functions. Until now, we have been differentiating various functions given in the form y is equal to f of x. But it is not necessary that functions are always expressed in this form. For example, consider one of the following relationships between x and y. X minus y minus pi is equal to 0. X plus sin xy minus y is equal to 0. In the first case, we can solve for y and rewrite the relationships as y is equal to x minus pi. In the second case, it does not seem that there is an easy way to solve for y. Nevertheless, there is no doubt about the dependence of y on x in either of the cases. When a relationship between x and y is expressed in a way that it is easy to solve for y and write y is equal to f of x, we say that y is given as an explicit function of x. In the latter case, it is implicit that y is a function of x, and we say that the relationship of the second type above gives function implicitly. In this subsection, we learn to differentiate implicit functions. Example, find dy by dx, except that y is defined in the appropriate region as a function of x. 2x plus 3y is equal to sin x. Solution, differentiating both sides with respect to x, we get 2 plus 3 dy by dx is equal to cos x. Therefore, dy by dx is equal to cos x minus 2 upon 3. Derivatives of inverse trigonometric functions. We remark that inverse trigonometric functions are continuous functions, but we will not prove this. Now, we use chain rule to find derivatives of these functions. Example 2. Find dy by dx y is equal to sin inverse 1 minus x square upon 1 plus x square, where 0 is less than x is less than 1. Solution, y is equal to sin inverse 1 minus x square upon 1 plus x square. Let x is equal to tan theta, which implies that theta is equal to tan inverse x. Therefore, y is equal to sin inverse 1 minus tan square theta upon 1 plus tan square theta is equal to sin inverse of cos 2 theta is equal to sin inverse sin pi by 2 minus 2 theta, equation 1. Now, 0 is less than x is less than 1. Therefore, tan 0 less than tan theta less than tan pi by 4. Therefore, 0 less than theta less than pi by 4. Therefore, 0 less than 2 theta less than pi by 2. Therefore, minus pi by 2 less than minus 2 theta less than 0. Therefore, minus pi by 2 plus pi by 2 less than pi by 2 minus 2 theta less than 0 plus pi by 2. Therefore, 0 less than pi by 2 minus 2 theta less than pi by 2. Equation 1, which implies that y is equal to sin inverse of sin pi by 2 minus 2 theta. Therefore, y is equal to pi by 2 minus 2 theta. Therefore, y is equal to pi by 2 minus 2 tan inverse x. Therefore, dy by dx is equal to minus 2 upon 1 plus x square. Exponential and logarithmic functions. The figure gives a sketch of y is equal to f1 of x is equal to x, y is equal to f2 of x is equal to x square, y is equal to f3 of x is equal to x cube, and y is equal to f4 of x is equal to x raised to 4. Observe that the curves get steeper as the power of x increases. Steeper the curve, faster is the rate of growth. What this means is that for a fixed increment in the value of x is greater than 1, the increment in the value of y is equal to fn of x increases as n increases 4, n is equal to 1, 2, 3, 4. It is conceivable that such a statement is true for all positive values of n, where fn of x is equal to x raised to n. Essentially, this means that the graph of y is equal to fn of x leans more towards the y-axis as n increases. For example, consider f10 of x is equal to x raised to 10 and f15 of x is equal to x raised to 15. If x increases from 1 to 2, f10 increases from 1 to 2 raised to 10, whereas f15 increases from 1 to 2 raised to 15. Thus, for the same increment in x, f15 grow faster than f10. Upshot of the above discussion is that the growth of polynomial functions is dependent on the degree of the polynomial function. Higher the degree, greater is the growth. The next natural question is there a function which grows faster than any polynomial function? The answer is in affirmative, and an example of such a function is y is equal to f of x is equal to 10 raised to x. Our claim is that this function f grows faster than fn of x is equal to x raised to n for any positive integer n. For example, we can prove that 10 raised to x grows faster than f100 of x is equal to x raised to 100. For large values of x, like x is equal to 10 cube, note that f100 of x is equal to 10 cube whole raised to 100 is equal to 10 raised to 300, whereas f of 10 cube is equal to 10 raised to 1000. Clearly, f of x is much greater than f100 of x. It is not difficult to prove that for all x is greater than 10 cube, f of x is greater than f100 of x. But we will not attempt to give a proof of this here. Similarly, by choosing large values of x, one can verify that f of x grows faster than fn of x for any positive integer n. Definition 3. The exponential function with positive base b is greater than 1 is the function y is equal to f of x is equal to b raised to x. The graph of y is equal to 10 raised to x is given in the figure. It is advised that the reader plots this graph for particular values of b like 2, 3 and 4. Following are some of the salient features of the exponential functions. Number 1. Domain of the exponential function is R, the set of all real numbers. Number 2. Range of the exponential function is the set of all positive real numbers. Number 3. The point 0, 1 is always on the graph of the exponential function. This is a restatement of the fact that b raised to 0 is equal to 1. For any real, b is greater than 1. Number 4. Exponential function is ever increasing. That is, as we move from left to right, the graph rises above. Number 5. For very large negative values of x, the exponential function is very close to 0. In other words, in the second quadrant, the graph approaches x-axis but never meets it. Exponential function with base 10 is called the common exponential function. In the appendix, it was observed that the sum of the series 1 plus 1 upon 1 factorial plus 1 upon 2 factorial plus up to so on is a number between 2 and 3 and is denoted by E. Using this E as the base, we obtain an extremely important exponential function y is equal to e raised to x. This is called natural exponential function. Definition 4. Let b is greater than 1 be a real number, then we say logarithm of a to base b is x. If b raised to x is equal to a, logarithm of a to base b is denoted by log of a to base b. Thus, log of a to base b is equal to x if b raised to x is equal to a. Let us work with a few explicit examples to get a feel for this. We know 2 cube is equal to 8. In terms of logarithms, we may rewrite this as log of 8 to base 2 is equal to 3. Similarly, 10 raised to 4 is equal to 10,000 is equivalent to saying log of 10,000 to base 10 is equal to 4. Also, 625 is equal to 5 raised to 4 is equal to 25 square is equivalent to saying log of 625 to base 5 is equal to 4 or log of 625 to base 25 is equal to 2. On a slightly more mature note, fixing a base b is greater than 1, we may look at logarithm as a function from positive real numbers to all real numbers. This function, called the logarithmic function, is defined by log to base b from r plus to r, x from log of x to base b is equal to y if b raised to y is equal to x. As before, if the base b is equal to 10, we say it is common logarithms, and if b is equal to e, then we say it is natural logarithms. Often, natural logarithm is denoted by ln. Log x denotes the logarithm function to base e. That is, ln x will be written as simply log x. The figure gives the plots of logarithm function to base 2, e and 10. Some of the important observations about the logarithm function to any base b is greater than 1 are listed below. Number 1. We cannot make a meaningful definition of logarithm of non-positive numbers, and hence the domain of log function is r plus. Number 2. The range of log function is the set of all real numbers. Number 3. The point 1, 0 is always on the graph of the log function. Number 4. The log function is ever increasing. That is, as we move from left to right, the graph rises above. Number 5. For x very near to 0, the value of log x can be made lesser than any given real number. In other words, in the fourth quadrant, the graph approaches y-axis but never meets it. Number 6. Figure gives the plot of y is equal to e raised to x and y is equal to ln x. It is of interest to observe that the two curves are the mirror images of each other reflected in the line y is equal to x. Two properties of log functions are proved below. Number 1. There is a standard change of base rule to obtain log of p to base a in terms of log of p to base b. Let log of p to base a is equal to alpha, log of p to base b is equal to beta, and log of a to base b is equal to gamma. This means a raised to alpha is equal to p, b raised to beta is equal to p, and b raised to gamma is equal to a. Substituting the third equation in the first one, we have b raised to gamma whole raised to alpha is equal to b raised to gamma alpha is equal to p. Using this in the second equation, we get b raised to beta is equal to p is equal to b raised to gamma alpha, where b is greater than 1, which implies beta is equal to alpha gamma or alpha is equal to beta upon gamma. But then log of p to base a is equal to log of p to base b upon log of a to base b. Number 2. Another interesting property of the log function is its effect on products. Let log of pq to base b is equal to alpha. Then b raised to alpha is equal to pq. If log of p to base b is equal to beta and log of q to base b is equal to gamma, then b raised to beta is equal to p and b raised to gamma is equal to q. But then b raised to alpha is equal to pq is equal to b raised to beta. B raised to gamma is equal to b raised to beta plus gamma, which implies alpha is equal to beta plus gamma. That is, log of pq to base b is equal to log of p to base b plus log of q to base b. A particularly interesting and important consequence of this is when p is equal to q. In this case, the above may be rewritten as log of p square to base b is equal to log of p to base b plus log of p to base b is equal to 2 log of p to base b. An easy generalization of this is log of p raised to n to base b is equal to n into log of p to base b for any positive integer n. In fact, this is true for any real number n, but we will not attempt to prove this. On the similar lines, the reader is invited to verify log of x upon y to base b is equal to log of x to base b minus log of y to base b. Example 1. It is true that x is equal to e raised to log x for all real x? Solution. First, observe that the domain of log function is set of all positive real numbers. So the above equation is not true for non-positive real numbers. Now, let y is equal to e raised to log x. If y is greater than 0, we may take logarithm which gives us log y is equal to log e raised to log x is equal to log x into log e is equal to log x. Thus, y is equal to x. Hence, x is equal to e raised to log x is true only for positive values of x. One of the striking properties of the natural exponential function in differential calculus is that it doesn't change during the process of differentiation. This is captured in the following theorem, whose proof we skip. Theorem 5. Number 1. The derivative of e raised to x with respect to x is e raised to x. That is, d by dx e raised to x is equal to e raised to x. Number 2. The derivative of log x with respect to x is 1 upon x. That is, d by dx log x is equal to 1 upon x. Number 1. The derivative of exponential function f of x is equal to e raised to x. If f of x is equal to e raised to x, then f dash of x is equal to limit delta x tends to 0 f of x plus delta x minus f of x upon delta x is equal to limit delta x tends to 0 e raised to x plus delta x minus e raised to x upon delta x is equal to e raised to x into limit delta x tends to 0 e raised to delta x minus 1 upon delta x is equal to e raised to x into 1. Because of limit x tends to 0 e raised to x minus 1 upon x is equal to 1 is equal to e raised to x. d by dx e raised to x is equal to e raised to x. Number 2. The derivative of logarithmic function f of x is equal to log of x to base e. F of x is equal to log of x to base e. F dash of x is equal to limit delta x tends to 0 log of x plus delta x to base e minus log of x to base e upon delta x is equal to limit delta x tends to 0 log of 1 plus delta x upon x to base e upon delta x is equal to limit delta x tends to 0 1 upon x into log of 1 plus delta x upon x to base e upon delta x upon x is equal to 1 upon x. Because of limit h tends to 0 log of 1 plus h to base e upon h is equal to 1. Thus d by dx log of x to base e is equal to 1 upon x. Example 2. Differentiate the function with respect to x. Number 1. E raised to x upon sin x. Y is equal to e raised to x upon sin x. Differentiate with respect to x. dy by dx is equal to d by dx e raised to x upon sin x is equal to sin x into d by dx e raised to x minus e raised to x into d by dx sin x upon sin square x using quotient rule is equal to sin x into e raised to x minus e raised to x into cos x upon sin square x is equal to e raised to x into sin x minus cos x upon sin square x, where x is not equal to n pi, n belongs to I. Number 2. E raised to x cube. Y is equal to e raised to x cube. Differentiate with respect to x. dy by dx is equal to d by dx e raised to x cube is equal to e raised to x cube into d by dx x cube is equal to e raised to x cube into 3x square is equal to 3x square into e raised to x cube. Number 3. Log of cos e raised to x. Y is equal to log of cos e raised to x. Differentiate with respect to x. dy by dx is equal to d by dx log of cos e raised to x is equal to 1 upon cos e raised to x into d by dx cos e raised to x is equal to 1 upon cos e raised to x into minus sin e raised to x d by dx into e raised to x is equal to minus sin e raised to x upon cos e raised to x into e raised to x is equal to minus e raised to x into tan e raised to x, where e raised to x is not equal to 2n plus 1 into pi by 2, where n belongs to n. Logarithmic differentiation. In this section, we will learn to differentiate certain special class of functions given in the form y is equal to f of x is equal to u of x raised to v of x. By taking logarithm to base e, the above may be rewritten as log y is equal to v of x into log u of x. Using chain rule, we may differentiate this to get 1 upon y dy by dx is equal to v of x into 1 upon u of x into u dash of x plus v dash of x into log u of x, which implies that dy by dx is equal to y into v of x upon u of x into u dash of x plus v dash of x into log u of x. The main point to be noted in this method is that f of x and u of x must always be positive, as otherwise their logarithms are not defined. This process of differentiation is known as logarithms differentiation and is illustrated by the following examples. Example 1. Differentiate square root of x minus 1 into x minus 2 upon x minus 3 into x minus 4 into x minus 5 with respect to x. Solution: y is equal to square root of x minus 1 into x minus 2 upon x minus 3 into x minus 4 into x minus 5. Taking logarithm on both sides, we have log y is equal to log into square root of x minus 1 into x minus 2 upon x minus 3 into x minus 4 into x minus 5. Therefore, log y is equal to 1 upon 2 log into x minus 1 into x minus 2 upon x minus 3 into x minus 4 into x minus 5. Therefore, log y is equal to 1 upon 2 into log x minus 1 into x minus 2 minus log x minus 3 into x minus 4 into x minus 5. Therefore, log y is equal to 1 upon 2 into log x minus 1 plus log x minus 2 minus log x minus 3 minus log x minus 4 minus log x minus 5. Now, differentiating both sides with respect to x, we get 1 upon y dy by dx is equal to 1 upon 2 into 1 upon x minus 1 plus 1 upon x minus 2 minus 1 upon x minus 3 minus 1 upon x minus 4 minus 1 upon x minus 5. Therefore, dy by dx is equal to 1 upon 2 into y into 1 upon x minus 1 plus 1 upon x minus 2 minus 1 upon x minus 3 minus 1 upon x minus 4 minus 1 upon x minus 5. Therefore, dy by dx is equal to 1 upon 2 into square root of x minus 1 into x minus 2 upon x minus 3 into x minus 4 into x minus 5 into 1 upon x minus 1 plus 1 upon x minus 2 minus 1 upon x minus 3 minus 1 upon x minus 4 minus 1 upon x minus 5. Example 2. Find dy by dx for the function x raised to y plus y raised to x is equal to 1. Solution: x raised to y plus y raised to x is equal to 1. Let u is equal to x raised to y and v is equal to y raised to x. Therefore, u plus v is equal to 1. Now, u is equal to x raised to y. Taking logarithm on both sides, we get log u is equal to y into log x. Differentiating both sides with respect to x, 1 upon u du by dx is equal to y d by dx log x plus log x d by dx y. Therefore, 1 upon u du by dx is equal to y upon x plus log x into dy by dx. Therefore, du by dx is equal to u into y upon x plus log x into dy by dx. Therefore, du by dx is equal to x raised to y into y upon x plus log x into dy by dx. Du by dx is equal to x raised to y minus 1 into y plus x raised to y into log x dy by dx. Equation 1. V is equal to y raised to x. Taking logarithm on both sides, log v is equal to x into log y. Differentiating both sides with respect to x, 1 upon v dv by dx is equal to x d by dx log y plus log y d by dx x. Therefore, dv by dx is equal to v into x into 1 upon y dy by dx plus log y. Therefore, dv by dx is equal to y raised to x into x upon y dy by dx plus log y. dv by dx is equal to y raised to x minus 1 into x dy by dx plus y raised to x log y. Equation 2. Now, u plus v is equal to 1. Therefore, du by dx plus dv by dx is equal to 0. From results 1 and 2, therefore, x raised to y minus 1 into y plus x raised to y into log x dy by dx plus y raised to x minus 1 into x dy by dx plus y raised to x log y is equal to 0. Therefore, dy by dx into x raised to y into log x plus y raised to x minus 1 into x is equal to minus y raised to x into log y minus x raised to y minus 1 into y. Therefore, dy by dx is equal to minus y raised to x into log y plus x raised to y minus 1 into y upon x raised to y into log x plus y raised to x minus 1 into x. Derivatives of functions in parametric forms. Sometimes the relation between two variables is neither explicit nor implicit, but some link of a third variable with each of the two variables separately establishes a relation between the first two variables. In such a situation, we say that the relation between them is expressed via a third variable. The third variable is called the parameter. More precisely, a relation expressed between two variables x and y in the form x is equal to f of t, y is equal to g of t is said to be parametric form with t as a parameter. In order to find derivative of a function in such form, we have by chain rule dy by dt is equal to dy by dx into dx by dt. dy by dx is equal to dy by dt upon dx by dt whenever dx by dt is not equal to 0. Thus, dy by dx is equal to g dash of t upon f dash of t, as dy by dt is equal to g dash of t and dx by dt is equal to f dash of t, provided f dash of t is not equal to 0. Example 1. If x is equal to 280 square, y is equal to 80 raised to 4, then find dy by dx. Solution: x is equal to 280 square, which implies that dx by dt is equal to 480. Y is equal to 80 raised to 4, which implies that dy by dt is equal to 480 cube. dy by dx is equal to dy by dt upon dx by dt is equal to 480 cube upon 480 is equal to t square. Example 2. If x is equal to cos theta minus cos 2 theta, y is equal to sin theta minus sin 2 theta, then find dy by dx. Solution: x is equal to cos theta minus cos 2 theta, which implies that dx by d theta is equal to minus sin theta plus 2 sin 2 theta. Y is equal to sin theta minus sin 2 theta, which implies that dy by d theta is equal to cos theta minus 2 cos 2 theta. Now, dy by dx is equal to dy by d theta upon dx by d theta is equal to cos theta minus 2 cos 2 theta upon minus sin theta plus 2 sin 2 theta is equal to cos theta minus 2 cos 2 theta upon 2 sin 2 theta minus sin theta. Second order derivative. Let y is equal to f of x. Then dy by dx is equal to f dash of x. Equation 1. If f dash of x is differentiable, we may differentiate 1 again with respect to x. Then the left hand side becomes d by dx into dy by dx, which is called the second order derivative of y with respect to x and is denoted by d square y by dx square. The second order derivative of f of x is denoted by f double dash of x. It is also denoted by d square y or y double dash or y2 if y is equal to f of x. We remark that higher order derivatives may be defined similarly. Example 1. When y is equal to x into cos x, then find d square y upon dx square. Solution. Given that y is equal to x into cos x. Now differentiating with respect to x, therefore dy by dx is equal to d by dx x into cos x. Therefore dy by dx is equal to x into minus sin x plus cos x into 1 is equal to minus x into sin x plus cos x. Again, differentiating with respect to x, we have d by dx into dy by dx is equal to d by dx into minus x sin x plus cos x. Therefore, d square y upon dx square is equal to minus x cos x minus sin x minus sin x. Therefore, d square y by dx square is equal to minus x cos x plus 2 sin x. Example 2. If e raised to y into x plus 1 is equal to 1, show that d square y by dx square is equal to dy by dx whole square. Solution. E raised to y into x plus 1 is equal to 1. Now, differentiating with respect to x, we get d by dx e raised to y into x plus 1 is equal to 1. X plus 1 d by dx e raised to y plus e raised to y d by dx x plus 1 is equal to d by dx 1. Therefore, x plus 1 into e raised to y into dy by dx plus e raised to y is equal to 0. Therefore, dy by dx is equal to minus 1 upon x plus 1. Equation 1. Again differentiate with respect to x, d by dx into dy by dx is equal to d by dx into minus 1 upon x plus 1. Therefore, d square y by dx square is equal to x plus 1 into 0 minus minus 1 upon x plus 1 whole square is equal to 1 upon x plus 1 whole square. Therefore, d square y by dx square is equal to dy by dx whole square because of from equation 1. Value theorem. In this section, we will state two fundamental results in calculus without proof. We shall also learn The geometric interpretation of these theorems. Theorem 6, Rolle's theorem. Let f from closed interval a, b to r be continuous on closed interval a, b and differentiable on open interval a, b such that f of a is equal to f of b, where a and b are some real numbers. Then there exists some c in open interval a, b such that f dash of c is equal to 0. In figure, graphs of a few typical differentiable functions satisfying the hypothesis of Rolle's theorem are given. Observe what happens to the slope of the tangent to the curve at various points between A and B. In each of the graphs, the slope becomes 0 at least at one point. That is precisely the claim of the Rolle's theorem, as the slope of the tangent at any point on the graph of y is equal to f of x is nothing but the derivative of f of x at that point. Theorem 7. Mean value theorem. Let f from closed interval a, b to r be a continuous function on closed interval a, b and differentiable on open interval a, b. Then there exists some c in open interval a, b such that f dash of c is equal to f of b minus f of a upon b minus a. Observe that the mean value theorem, that is MVT, is an extension of Rolle's theorem. Let us now understand a geometric interpretation of the mean value theorem. The graph of a function y is equal to f of x is given in the figure. We have already interpreted f dash of c as the slope of the tangent to the curve y is equal to f of x at c, f of c. From the figure, it is clear that f of b minus f of a upon b minus a is the slope of the secant drawn between a, f of a, and b, f of b. The mean value theorem states that there is a point c in open interval a, b such that the slope of the tangent at c, f of c, is same as the slope of the secant between a, f of a, and b, f of b. In other words, there is a point c in open interval a, b such that the tangent at c, f of c, is parallel to the secant between a, f of a, and b, f of b. Example 1. Verify Rolle's theorem for the function f of x is equal to x square plus 2x minus 8, where x belongs to closed interval minus 4, 2. Solution: f of x is equal to x square plus 2x minus 8, where x belongs to closed interval minus 4, 2. Here the function f of x is polynomial. It is continuous in closed interval minus 4, 2. F dash of x is equal to 2x plus 2. F dash of x exists in closed interval minus 4, 2. So f of x is differentiable in open interval minus 4, 2. F of minus 4 is equal to minus 4 square plus 2 into minus 4 minus 8 is equal to 16 minus 8 is equal to 0. F of 2 is equal to 2 square plus 2 into 2 minus 8 is equal to 4 plus 4 minus 8 is equal to 0. Therefore, f of minus 4 is equal to f of 2. All the conditions of Rolle's theorem holds. C belongs to open interval minus 4, 2 such that f dash of c is equal to 0. Therefore, 2c plus 2 is equal to 0, which implies that c is equal to minus 1 and minus 1 belongs to open interval minus 4, 2. Hence, the Rolle's theorem is verified for the function f of x is equal to x square plus 2x minus 8, where x belongs to closed interval minus 4, 2. Example 2. Verify mean value theorem if f of x is equal to x square minus 4x minus 3 in the interval closed interval a, b, where a is equal to 1 and b is equal to 4. Solution. The function f of x is equal to x square minus 4x minus 3 is continuous on closed interval 1, 4. As f of x is a polynomial, f dash of x is equal to 2x minus 4. F dash of x exists in open interval 1, 4. So, f of x is differentiable in open interval 1, 4. According to mean value theorem, there exists c belongs to open interval 1, 4, such that f dash of c is equal to f of 4 minus f of 1 upon 4 minus 1. Now, f of 4 is equal to 4 square minus 4 into 4 minus 3 is equal to 16 minus 16 minus 3 is equal to minus 3. F of 1 is equal to 1 square minus 4 into 1 minus 3 is equal to 1 minus 4 minus 3 is equal to minus 6. Therefore, f dash of c is equal to f of 4 minus f of 1 upon 4 minus 1. Therefore, 2c minus 4 is equal to minus 3 minus minus 6 upon 3. Therefore, 2c minus 4 is equal to minus 3 plus 6 upon 3. Therefore, 2c minus 4 is equal to 1, which implies that c is equal to 5 upon 2 belongs to open interval 1, 4.